Okay, so I was under the impression that most of the people are definitely familiar with deep learning, but not much maybe NLP. But after the talk that we had in the past, I think I changed my mind. But excuse me if it's going a little bit too basic for you guys, but hopefully it quickly gets advanced. So for those of you who are not familiar with natural language processing, basically it's a collection of techniques that enables machines to understand, analyze the human language, and even furthermore be able to generate human-like language. May by show of hands see how many people are working in the NLP area? Okay, and how many people are clinicians here? Okay, so I just want to have a disclaimer. I put some reports, the radiology notes there. I made it up. So if it just doesn't make sense, excuse me for that. But hopefully it's not too far. So there are lots of different levels that you can do NLP in general. I'm not talking about healthcare. But just to kind of summarize them, you can categorize them under these 4 categories. The first level will be morphological analysis. So this is to deal with the word structure, like making adverbs, adjectives out of a base word. The next level would be syntactic analysis. So this is the grammar, the grammar of the language. A little bit more advanced, then you talk about semantic analysis, and that's now you're trying to take into account the meaning of the words with the immediate context. And the immediate context would be the sentence that the word is occurring in. And as you can imagine, this is getting harder and harder problem for a machine to kind of learn. And then at the end, the pragmatic analysis, which is the meaning of the words within a context. So now you're talking about a piece of text, a paragraph, or a whole page, that this word with respect to that, the meaning of it and the interpretation might change. In healthcare, actually, NLP has gained quite a bit of interest, and this is due to the fact that a lot of information is being captured by clinicians in the form of text, besides the images that are taken from the patients. But interpretation of those basically findings are given to us by the clinician in the form of text. There are lots of different applications how we can leverage that information being captured in the notes, discharge notes, radiology reports. I just sum up a few of them here, but the list can go on. So there's a lot of issues with the unstructuredness of the data. So some hospitals, some clinical sites use some sort of a template to start with to capture the information about the patient, but that is due to the fact that there are lots of variability from one site to another, or like clinicians also on the fly, they may change the structure. That kind of raises the issue of being the unstructured data to deal with. And I just put an example, the clinicians spend like 49% of their time on paperwork and kind of getting these data organized so that next time they come to the same patient, they can take advantage of it. The other kind of very hot topic would be decision support. So this is something that FDA is very sensitive about, of course, but there are some successful examples we have seen so far that they can take advantage of the information being provided about the patients and be able to learn some patterns and rules, and then kind of help the clinicians to kind of as an assistant or like a help from the shoulder to make a better decision, or like kind of digest the information for you so the decisions can be more straightforward. So in 2013, the Department of Veteran Affairs used NLP to review more than 2 billion EHR documents, and basically to look at indications of PTSD, depression, etc. And they have shown some promising results in that as well, that this could be used for decision support. And then finally, the last application that I put is for Q&A. I don't know if you have guys seen the radiologist work, but there's a lot of back and forth between different workstations. One is providing you the EHR data, one is about the image. And then as they look at the patient's record, they kind of gain these insights about the patient. But what if we have a Q&A system that if you just want to know the patient had any asthma or any allergies in the past, you can just pop the question, and then the machine behind the scene crawls the data and be able to give you that answer on the fly. And I put one example of that. Rasuf, Chief Innovation Officer at UPMC, basically use NLP apps. They're doing a lot of NLP activities these days that to take advantage of it and reduce the time needed to uncover valuable insights from their data. So what are the challenges that basically applying NLP in healthcare is facing these days. I list a few of them here, and hopefully captures most of the things that you guys have run into as well. So the first thing I put is the data size. And as I said, pretty much every day, thousands of patients are visiting sites, and each of those patients are being either imaged or kind of gone through some lab results, and all that information is, the format is currently uniquely being used across all clinical sites would be the text format. So there's a ton of data being generated on the fly. How to organize this, structure it, that's a big headache definitely for NLP. The data source and format, this is related to interoperability. So if you use Epic versus some other system to capture this data, they are not very compatible with each other. So if you get data from different sources, you want to feed it to your NLP, you need to worry about the same format, or you're going to basically need to do some pre-processing before you'll be able to pass the data to your machine learning algorithms. And the next would be the data structure. So basically, there's not much of a structure there, so that makes it even harder for NLP to look for patterns of redundancy to learn from. The longitudinal data, so the historical data is very important to do the decision making for the clinicians, and being able to look at the data at different time points, that's something that NLP can help, but of course it's a challenge and it's a difficult problem. To give you an example, let's say you see a report of a nodule in the lung, you want to see what has happened in the past about it, to be able to locate the same nodule in the text that they talked about it in the previous data, that's a difficult problem. And then the clinical language, the complexity of it, as with all due respect, but there's not much grammar going on in the radiology reports, as well as there are lots of telegraphic way of describing things and abbreviations that are not found in the standard ontologies. These are all like just adding to the complexity of the NLP that you are trying to build. And then the ambiguity, so there's negation in the report, there's speculation, and all those you need to take into account. So if there's someone interested to know if there is a nodule, if they say there is no nodule, you should be able to differentiate that versus the existence of a nodule, for instance. And then finally, I put this one as the last bullet point, the experience-driven domain knowledge. So when I'm talking to clinician, there's lots of books that they learn from to practice, but it turns out that there's a lot that they learn on the job. And those are things that it might change from one clinician to another, and as a result, the variability in the data we will see. So then the data will have different senses. So if you give the same patient to, or the same, let's say, even image to multiple radiologists, they might annotate the data, label the data differently because of this experience level. Something might look significant to one radiologist and not to the other one. So among all the basic tools and techniques in NLP, I thought I can focus on name entity recognition. And I'll tell you in a second what does it mean. But this is one of the hottest topics these days as one of the main building blocks for building any NLP kind of pipeline. So what does name entity recognition mean? Basically, it's a bunch of techniques, helps you to classify entities meaning, let's say, words, phrases, in a piece of text using some predefined categories. So to give you an example, I put a piece of a radiology report here. As you can see, I'm tagging the anatomical terms in this piece of text. And the label that I'm talking about, that would be anatomical structures. So you can define the same categories for all the other things, for instance, the findings, nodule, or the diagnosis, etc. There are approaches proposed to deal with and then solve this name entity recognition or NER problems. I divide them to pre-AI and post-AI. So starting from the traditional approaches, you build a dictionary, a bunch of keywords based on what you have seen in the past, and you look for exact matches. Or if you want to do a little bit of more smart way of matching, you can deal with typos, deal with like some sort of plural versus singular format. So I give an example here, that you can see. This is a snapshot from the SNOMED ontology. It's a browser available online. So if I put the left lower lobe of lung, then I can see exact matches or almost exact matches that pops up. And for this example, I can detect that one. But what if I have something like right lobe of long. So if I look in the ontology, let's going back to the previous slide, I can see that that doesn't exist as is. So I cannot get it with the exact match. So I can define some grammars and rules which are typically implemented with regular expressions. This is a kind of a programming, a tiny programming that you can do that allows some specific values to be able to match or not. So you can still be able to detect these using this kind of phrase using regular expressions. A little bit more advanced, what about, we see some abbreviations like this, RUL, referring to right upper lobe of both lungs. So, by the way, this is the radiology report that I said I made it up. But basically here, then maybe you can start looking into some statistical machine learning, such as CRFs, SVMs, etc. And there you need, obviously, it starts to look like you need some training data, right? So you need to prepare some annotated data, and within your annotated data, you should be able to see at least good enough variations that you're hoping to capture with your NLP tool. But it comes to points that you will see some stuff that you never seen in the previous training data that you prepared, and that's where I call it the PostAI comes into play. We have seen a lot of successful stories with that, and I'm going to walk through a few of them. But just to start with, basically since the development and proposal of the RNN networks, different flavors of it, and CNN networks, we have seen that they can take advantage of this to address some of the shortcomings of the more traditional approaches that I mentioned in the previous slides. I put this chart here because if I want to kind of look at it in terms of the progress that has been made, they're like ancient approaches that I just described, but then since the introduction of the RNNs and CNNs, we start seeing this importance of the distributed representations. As Janusz was talking about the fact that these word embeddings are a way of getting machines to understand the text. So as Janusz mentioned, you bring the string representation of text in the form of a numeric vector representation in a high dimensional space. So word2vec was introduced a while ago. After that, more recently in 2018 and 19, we heard about the Elmo and BERT models. These are kind of taking advantage of the language modeling, and that's where kind of we see a lot of boost in the results of the NLP applications. So I'm just going to quickly walk through some of the history about these embedding representations. Probably some of you are familiar with the continuous backward skipgrams that basically, given a context, you're trying to predict a word, so that's what you're training on. But what you get out of this, not just the prediction part, but take advantage of the smaller, shorter representations that this is being captured by this prediction model. So those are going to give the word representations to you. So if you like, for instance, this is a paper that we published a few years ago. This is the SNOMED ontology for a bunch of anatomical terms. Every dot in this plot represents an anatomical term from the ontology. The ones that are the same color, they correspond to the same anatomical structure, such as lung, brain, thyroid, etc. So if you look at it, for instance, the brain will be represented by a vector versus liver, and a compartment within the liver is going to have a representation close to that. But what if I tell you about something like, for instance, lobe, right? Lobe is something that can happen in thyroid, can exist in the lung, can exist in the liver. With the approach that I just showed you, the word2vec approach, it finds based on the most frequent occurrence of that word with lung or liver, etc. And as a result, you can see when we applied such technique, we see that, for instance, for the lung, it gets it corrected, left lobe, even though there's not saying anything about the lung in the neighborhood of it, but it detected it correctly. This is related to the lung. But if you look at, for instance, the case of brain, because the vector representation was closer to the lung or liver, it tried to predict it as a liver. So these are the mistakes that you see because of this fixed context learning happens. So we trained, for instance, LSTM bidirectional model, and that's the output that you can see, taking advantage of the word embedding that are fixed based on the content. Now, to basically overcome that problem, what we did, basically, we started looking into more advanced approaches. So for instance, instead of having one bidirectional LSTM, we have another one that learns just the context. So you input the words in a sentence into both of them. One of them is going to tell you at the end, what is this whole thing talking about? Is it talking about lung, liver, etc.? And then that is going to give you a feature. That feature gets added to the feature word level feature representation. And then you're going to give token level or word level annotations for your piece of text. So this approach started to overcome some of the problems I showed. But then at the end of the day, there are scenarios that the context that occurs next to it, it's a bit further away to give you the right label. So let's say if it was not mentioned the right lobe of liver in the same sentence, maybe in 2 sentences before that. So how do I take advantage of that context to be able to label this scenario? So for that one, we start looking into Elmo and BERT, which are language models. To just give you a quick summary, what does they do is basically you train the algorithm to learn to speak English. Just like you start from teaching your child how to speak English. Once they're okay to speak English, now you go teach them radiology language. So you retrain the few layers, what you typically do in the CNN for the image processing. You erase the last few layers, and then you retrain them with your specific label data. The good thing is that you need minimal label data for doing this, because majority of it is learned from a corpus that doesn't need to be labeled, and that would be giving you the language model. So with that scenario, based on the context that is occurring around it, let's say if I divide the space like this, so we have a part of the space that is talking about anatomy, a part about tests and findings. If I'm given lobe, then based on the context around it, is going to either take it closer, the representation, to the brain or lung or liver, according to the adjacent context. So for that, what we did was basically, now we start using multiple bidirectional LSTMs, that every sentence in the report goes to it, and then all of them is going to help you get a better understanding of the context to give you final labels. So at the end, I just want to finish with the fact that this is one piece of the puzzle I just talked about, which would be anatomical phrase labeling. But obviously, there are lots of different NERs we need to prepare to build a tool that eventually solving a healthcare problem, but it's not done yet. After that, we need to look at the attributes. Are they negated? Are they speculated? We need to look at the timestamp. Are they important or they're way too in the past? So longitudinal data analysis. And finally, domain knowledge. And that comes very expensively, learning based on every individual's experience, that this type of nodule, this size, does it really matter or not? So do I want to take that into account to my NLP tooling or not? So I would leave it at this, and I'm happy to answer any questions.